Alright, in this video we're going to discuss the polar form of complex numbers. So to begin, we're going to talk about what's called the complex plane, which looks very similar to, say, the rectangular coordinate system that you're all used to. The one difference that we're going to make here is that the axes are going to be labeled slightly different. This is called the real axis. We're going to call it X here. And this one's going to be called the imaginary axis. We're going to call it y, I. Okay. All right. So complex numbers can't be ordered like real numbers can, right? Because remember, complex numbers have two parts. If a and b are real numbers, then the rectangular form of a complex number looks like a plus bi. Okay. And remember, it's got a real part and an imaginary part. So we can graph complex numbers on the complex plane with the real axis, the imaginary axis. And those are going to correspond to the real part and the imaginary part. So for example, a plus bi, we would go over a and we would go up whatever b is. For example, and just say plot there. That would be the point a plus bi. This is a and this is b. Now we typically use the following notation. Z to be equal to your complex number a plus bi. So we'll just say the complex number is z, right? Whatever z is defined to be, and it'll be of the form a plus bi. And so what that leaves us here, we've got this vector that goes out from the origin to the complex number. So the absolute value of a complex number z would be equal to, well, that's just the Pythagorean theorem, right? And you'd have the square root of a squared plus b squared. Because remember, the absolute value of a number can be defined to be its distance from zero, right, so to speak, or its distance from the origin is another way you can think about that, right? So we're just saying, when we use this notation, how far is this number z away from the origin? Well, that would be the hypotenuse of this right triangle here, and that's easy to figure out what that distance would be. Now, a little note then. Each complex number, a plus bi, does determine a vector, right, with the initial point at the origin and the terminal point out here at a plus bi. So no matter where you plot a complex number, that determines a vector. All right, so now let's look at a note. We're going to let z equal x plus yi. Get this right triangle going on here. This is theta, and this distance is r, just from previous knowledge. Okay, so now we've got this triangle that corresponds to this complex number. So if z equals x plus yi, then x is equal to r cosine theta. Remember that? And y is equal to r sine theta. Okay, r turns out to be the square root of x squared plus y squared. And then the tangent of theta is y over x, provided x is not 0. All that should look familiar from when we were playing with right triangles and trig, right? All we're doing is expanding that out to the complex plane. Okay, so these four things here are going to be important to remember. Now, if we take x equals r cosine theta and y equals r sine theta and substitute that into our complex number up here, z equals x plus yi, we get the following. It's called the trigonometric or the polar form of a complex number. And you get z equals r cosine theta plus I r sine theta, and you end up factoring the r out. And so that's why it looks like this. Z equals r times cosine theta plus I sine theta. I've also seen it look like this. Z equals r cis theta. It's kind of like a shorthand notation. R equals cis of theta. So if you got a book that's using that, or you have an instructor that uses that notation, that's where that's coming from. Okay, the r is called the modulus of z, which is really the absolute value of z. And theta is called an argument of z. All right, so let's write z equals negative 5 minus 5i in polar form. So in order to write it in polar form, we need to find r and theta. Okay, so r is easy. R equals the square root of negative 5 squared plus the other negative 5 squared. So r equals the square root of 50, which is 5 square root of 2. Now, What quadrant is your complex number in? Z is located in quadrant. Well, the x is negative, the y is negative, so we're located in quadrant 3. Right, so what I'm going to do is find the reference angle and then use that to figure out what the angle is in quadrant 3. All right, let's find the tangent of theta hat for the reference angle. And I'm going to make everything positive. So when I do that, you get 5 over 5, which equals 1. So the tangent of theta hat equals 1, which implies that theta hat is equal to pi over 4. That'd be the reference angle. So since we're in quadrant 3 here, that implies that theta is equal to 5 pi over 4. So z is equal to 5 square root of 2 r times the cosine of 5 pi over 4 plus I sine 5 pi over 4. And that is the trigonometric form, or the polar form of the complex number. Now you might be thinking that big deal that looks worse than the negative 5 minus 5i. And while I agree it looks worse, it can be easier to play with. Okay, we'll get to that in a little bit later. Alright, so now let's try this one. Alright, let's write z equals 4 times cosine 60 degrees plus I sine 60 degrees into rectangular form. Well, to do that, you just kind of do it. So z equals 4. What's the cosine of 60 degrees? Well, it's a half. And what's the sine of 60 degrees? Well, it's the square root of 3 over 2. So z is equal to 2 plus 2i radical 3. That would be its rectangular form. All right, so now we're going to multiply complex numbers together. Suppose we have two complex numbers. I'm just using the subscripts here to denote we've got different angles and different r's. Right? So when we multiply z1 times z2, then you get r1 times r2, and we're going to get this binomial times that binomial. If you FOIL that out, you would get that. Notice this is negative sine theta 1 sine theta 2 because you have an I times an I, which would be I squared, which goes to a negative 1. That's why that happens there. All right, now let's move things around. Okay, so we've grouped the things that had an I and the things that did not have an I. All right, so this part right here is one thing, and this part here is another thing. We'll just factor the I out. When we do that, we can rewrite cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2 from a trig identity as cosine of theta 1 plus theta 2. And then this part right here goes to the sine of theta 1 plus theta 2. So to take two complex numbers that are written in polar form and multiply them together, it's as simple as doing the r1 times r2, take each modulus, multiply them together, and then take the cosine of the sum of the two angles plus I sine of the sum of the two angles. For example, z1 times z2 goes to 4 times 5, which gives you 20. The cosine of 30 degrees plus 120 degrees, that's where this 150 degrees is coming from. And then the sine of 150 degrees. And then when you figure out the cosine of 150 degrees goes to the negative square root of 3 over 2. Sine of 150 degrees goes to 1/2. And you've just multiplied these two complex numbers together to get negative 10 radical 3 plus 10i. So it can make multiplying complex numbers together kind of easy. All right, so to summarize, we've got the product and the quotient of two complex numbers. Now I'm not going to derive the quotient idea, but you can do that on your own. If z1 is equal to r1 cosine theta 1 plus I sine theta 1, and z2 is equal to r2 plus cosine theta 2 plus I sine theta 2, then the product z1 times z2 we've already discussed. All right, so now the quotient z1 divided by z2, it's kind of similar. We're going to have r1 divided by r2. That makes sense. And then we, instead of having the sum of two angles, we're going to have their difference. So it'll be the cosine of theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. This is all provided, of course, z2, the one that's in the denominator, does not equal 0. All right, and this identity follows. You can prove this on your own if you would like. All right, so that's the idea of taking a number that's in rectangular form and writing it in polar form. That idea will help us when we raise complex numbers to powers, as well as take roots of complex numbers. And that'll be in the next video. Study well. Please let me know if you have any questions.